Hello and welcome everyone. My goal today is to go over this surveying notes packet. And by surveying, I mean not just, any kind of general, survey class or, go and survey the site, although closer to that. We're talking about land surveying, so the actual skill in which there are many people who are active professionals of measuring the Earth's surface. So surveying is important in modern times for figuring out where to put pipes, where to build buildings, making sure that walls are being put in the right places. It's also used very, very often to create maps of the landscape, to create maps of rivers and streams and forests and so forth. And today I'm going to go over an introduction that's going to cover both the kind of simple and lower tech approaches. Let's get that little blip out of the way. So simple, low-tech approaches, as well as higher-tech surveying methods that we have that are up and coming, things like real-time kinematic GNSS units. So these old technologies and techniques are still actually quite important, and I feel like they're very educational, so we're going to go through them. And Compton's classic Geology in the Field book has a useful basic introduction to some of these topics, and I suggest that this is a resource that you look up in the library if you have some further questions. So first off, let's start out with by imagining a scenario. You're out in the field, maybe in a forest, maybe in a desert, maybe on the plains, and you see a feature of interest. Maybe it's a hill or a river or this place where this meteorite crashed into the ground that you have to survey, and you want to know where it is. And of course, that really simple question of where is it requires knowledge of how your position relates to other objects around the globe. So because you need to have that much knowledge, it's really hard to be standing, let's say, in the middle of Kansas and say, where am I with respect to the Azores, the Virgin Islands, and Namibia, right? It's just is really difficult. That's why we have global positioning satellites, and we're going to get to that later. However, oftentimes you just need to know where one thing is with respect to another thing. And that's where a lot of surveying comes into play, where what we really want to do is have a local relative system of coordinates. You'd think I could underline a little bit better. Relative system. There we go. The pad was slanted. Relative system of coordinates. And that is commonly our approach. So, scrolling down. So we can make this relative coordinate system with respect to any feature, but typically we're focusing on something that's recognizable, right? So we can see it again, and something that's expected to be permanent. So for example, a tree might not be the greatest because trees grow and trees get blown down in storms. However, the top of a large prominent boulder might be a good point, or a large stone building. So in surveying, we typically, if we're trying to mark a position on the ground, which is also often a good spot, we'll mark it with some survey stakes. Oh. Bear with me as I just learn how to use this whole thing. So what we do is we pound the stake into a ground at a desired point, and then we add a nail and a marker. And so here's what it's going to look like. So we have, let's say this is the land surface right here. This is the ground. And what we do is we pound in this survey stake with a hammer until its top is flush with the ground surface, more or less. We then add a piece of flagging, and so this could be some kind of ribbon or something that's brightly colored that comes off of that survey stake. And that's quite important to us because it helps us to find it. And then on top of that, we put a nail that holds it in, big colored in spike. And this nail is important because it holds in that survey stake, holds this flagging into the survey stake, and also provides a point right here which often has a divot, into which you can place your survey rod. And that means that whenever you're sticking this rod in, which you're using to measure positions, you're measuring it from or to the exact same location. So that's the rod, this is the flagging. Here's the stake. And then this is, of course, just the ground. All right. So if you're trying to think about obtaining absolute positioning, you need one of a few methods. The first one is a precise measurement with respect to known benchmarks. So let's say if you have, some actual survey benchmarks, like you might see on the top of a mountain. And this is an example right here. So this is a benchmark that's put in by surveyors, and you can see 769 feet above sea level. And it's put in by the United States Geological Survey. Sometimes you'll see them from the Coast and Geodetic Survey. And this was put in 1956. And this right here, this little thing here, this is the point in which your survey rod would go. Right there. So that's one option. So, and you can use, another option is GNSS, so Global Navigation Satellite System, of which there's, for example, the GPS satellites of the US, GLONASS, which is the Russian one, and new satellite constellations by China and Europe are coming online as well. So what you can do is combine then these absolute position measurements with the much more precise relative measurements between points that you can obtain with classic surveying techniques to build a consistent and georeferenced data set that you can then pull into a geographic information system, in other words, a GIS, and start to build some knowledge about what you're looking at in a particular area, or be able to locate samples with respect to one another, be able to locate water wells or stream banks or the edge of a lake, and so forth. So improvements in GNSS are actually starting to bring these absolute measurements close to or better than sometimes traditional analog surveying equipment. But some of the digital survey equipment that we'll talk about retain higher precisions. So starting off then, what's the most important basic thing that we can have in order to measure distance? And that's just a measuring tape. And what is that? That's just a piece of rope or webbing or some sort of flat fibrous thing that has increments marked out on it, and we can use it to measure distance. And they're often called a surveyor's rope. They can also just be called a tape. And when they're tight, they give a straight line distance between 2 points. One thing to note is that when crossing the ground, these systems will give the longer measure between 2 points because it might be going along the land surface. In other words, if I am up here and my friend is down here, and she's holding a tape right here, and then in order to compare where our positions against one another, I start to pull it out this way until it's nice and tight. But here's the problem, is that if it's like this and this is like 50 meters, this thing is going to be swinging back and forth in the wind like crazy. So instead, we put it on the ground. So I'll just draw another quick image. So there's me, there's the partner. And so if we have the tape on the ground between us, the tape is also following these contours of the ground. And so this distance, so I'll call this L prime, and I'll call this distance L. And what we know is that L prime has to be greater than L because it follows a curved in other words, indirect path. And so that's just one thing to be aware of. And so let's just imagine, for example, that you're taping up a slope that you know to be 5 degrees. So if you've read a tape on that's 10 meters, you know, what's the horizontal distance between these points? And so you can do that just fine if you have, you know, if you're just dealing with a straight slope like this, that's no problem. You can just figure this out with trig. But the whole idea is that then if this is a 5-degree slope, but also bumpy, so with that instead of this, then that's going to be a little bit more difficult, right? Because you're not going to get a nice straight line distance. And here's an example here. So on the left-hand side, this is a surveyor's rope. And on the right-hand side, this is a tape. And at the University of Minnesota, we have both of these. So taping is accurate, but it has one disadvantage in that it takes time to string that out and hold it and keep it tight and making sure that you know exactly where it is. And so if you're trying to measure just distance across the surface, pacing is really useful. And someone who's skilled at pacing can actually estimate distance to about 1% accuracy. And you can do it by just walking and counting your steps. So this is actually going to be one of the activities that you might be assigned. And in fact, when I'm in the year in which I'm recording this video, 2020, you will be assigned. And this is to figure out what your pace is. And that's because this is just a really useful piece of information to know. So I want you to lay out a 100-meter tape or rope or another distance measurement tool of your choice. I realize that this year many of you might be doing this by yourselves. In future years that might not be the case. But when you're doing this, if you're doing it by yourself, what you can do is just map out a convenient and walkable distance between two recognizable points using Google Earth, in which you can use the measurement tool to figure out that distance, and then use that to figure out what your pace is. So after you do that, what you need to do is just walk along that tape or that distance and take normal steps. Write down the number of steps it takes, and then figure out the length of your stride. Pretty simple. So just look through that. All right, in addition to taping and these methods, another method that we have is using laser rangefinders. So handheld models of laser rangefinders can typically mark distance to plus or minus 10 centimeters. And so let's think about that in terms of pacing, right? So if 10 centimeters is equal to 0.1 meters, and if you have 1% accuracy when you're pacing, what this means is that if you pace 10 meters, you're going to be close to, you're going to be 10 meters plus or minus 10 centimeters pacing. And so that is going to give you kind of, if you're shooting to a target about 10 meters away, this laser rangefinder is going to have about the exact same accuracy as you would if you're skilled at pacing, with the big advantage that you don't actually have to pace that distance out. You can just shoot at it. So technology can be your friend. So these simple laser rangefinders are accurate to plus or minus 10 centimeters. High precision ones, though, including those in a total station, which we'll talk about below, can be precise to about 1 millimeter. And now that, if you wanted to compare this, so if you went 100 millimeters, so 10 centimeters, then you would have the same error in your pace as you would with the total station. And so for anything longer than that, the total station is going to win out. It's an excellent piece of equipment. So high precision laser rangefinders have also been integrated in what we call LiDAR, so light detection and ranging technology. And these are responsible for distance measurements in robots and in experimental self-driving vehicles. We'll see how long they stay experimental if I keep using this video. And as well as airborne LiDAR. So this is the way that we actually get topographic maps, including the ones that we have of the state of Minnesota. And we also use high-precision terrestrial laser scanners. So lasers are incredibly useful and are a surveyor's friend. So lasers give us distance, and the way that they do is they give us this two-way travel time. We shoot, they reflect off something, they come back to us. But they don't tell us the angle, and so we need to have some way of measuring inclination, so which is the angle from the vertical. And it can be measured with a variety of analog instruments or digital instruments. So first off, let's just look at analog instruments, because many of you might have some background in geology or archaeology or one of the other ologies in which you like to measure things, and so therefore you might have actually used something called a Brenton pocket transit, or more likely, you just call it a Brenton before. And these kinds of compasses contain bubble levels, which help you get an angle. And so you can swing this thing, so this bubble level is attached to this measurement piece down here. And as you swing it back and forth, and if you have the compass itself set up on a particular surface with a particular angle, you'll end up figuring out what that angle is by finding out how much do you need to move it in order to get this bubble back into the middle over there. And so that, in fact, if the bubble's over here, right, you actually would have to move it this way, and then the slope would have to be the other direction. But I wasn't thinking about that when I drew that line now, was I? So that's the Brenton pocket transit, and there's a bit of information here on how to use it. I'm going to leave that for you to read. You can also use a handheld clinometer, and that's an instrument that you hold up to your eye, and then it will read the inclination when you're looking across another feature. Again, these analog instruments are important. Laser rangefinders, some of these have digital clinometers, and a level transit is a very important piece of information. So this is a surveying device capable of measuring both distance and inclination. And so it's good for measuring relative vertical positions of surfaces. It's used very often, therefore, for things like groundwater wells, or situations in which you have placed a transect or like a measuring tape across a river, and all you need to know is what the vertical elevation is. Because then if you know what the vertical angle is from the transit, so here's your level transit. And so if you know what the distance is and what the angle is, right? So then you know this dist, and you also know this angle alpha. Then it's just a simple matter of trigonometric functions to find this delta z, this elevation right there. And that's oftentimes just the only thing that you actually want to know. So section 4 here is an exercise that I'm just going to briefly go over. The idea here is that you're doing a leveling survey across a river, and we have some example data points, and also have some examples of, potential error that might be associated with them and how to compute error. So while working through this and the error computations, I would suggest that you think, maybe use a spreadsheet, use some pencil and paper, but this is designed to introduce you to the general idea of how errors actually accumulate over the course of a survey. And so we have, these basic pieces of information on calculating error, and there we go. And after this, there's also another exercise in trying to understand and sketch the cross-section across the river. This just follows right on from that survey. And if you want to know what the definition of a cross-section is, so if there's a river that's flowing this way, if you have a line right here from A to A prime, so I'm going to draw this here now, A prime, and so we're going to say that this is north, this is east, and so now here we have just A to A prime, and then we have the up axis here is Z, which is elevation. And so on this A to A prime axis, what you need to do is draw, what you think this river looks like in profile, in topographic profile. All right, so we've talked about measuring distances and vertical angles, and with distances and vertical angles or inclinations, we can perform a leveling survey across a river. We can know what elevations things are, but While we can construct these one-dimensional topographic profiles, it would be way more helpful if we could place these data actually in a map in space in X, Y, and Z, or easting, northing, and elevation. And so what we need to do is be able to have angles in the horizontal as well. And so how do we do this? How do we set the coordinate system? And there are a couple of main methods. So we can set it based on a angle that's aligned with true north, right, such that 0 degrees in our instrument just aligns with true north. We know exactly where north is. Great. We're happy. But that's not always possible. And so oftentimes we'll go instead with an angle that's arbitrary. And so we'll just pick like, we're just going to call this 0 degrees. We're going to go with it. And we'll just figure it out from there. And both these methods can be fine. Just know that the second method is going to be a little bit more tricky to reconstruct with respect to an absolute coordinate system. And so just like I was saying before, we have easting, which is x. So I'm just going to write this out just so we have this down. We have northing, which is like our y coordinate. And then we have elevation, which is our z coordinate. So z is z. And you can think about this in terms of a coordinate system. So we have easting, which is x, northing, which is y, and coming up towards us. And so remember, this is the tip of the arrow coming towards us. This is elevation, which is just z. And as you can see, if you put your index finger towards the E, I'm doing it, but you can't see me, your middle finger 90 degrees away from it towards the N, and I'm assuming that you're putting it 90 degrees away towards your palm as you're closing your finger. If you really are that good at pulling your finger backwards, please just do it the other way. Then we'll have a proper right-handed coordinate system. And then your finger with Z is going to be your thumb, and that will be pointing upwards. And so we see that we're obeying the right-hand rule. We have a right-handed conventional coordinate system. We're all set. So azimuth is the angle away from north. And so if we're thinking about this then, so we have up here, this is going to be 0 degrees. An angle going east is going to be 90 degrees. South is 180 degrees, and west is 270 degrees, which means that north is actually also 360 degrees, but we never mark anything as 360 degrees. We always just go back to 0. So a compass is one of the first and most useful tools that we use for this kind of measurement. And if we want to use a compass to be able to tell directions and tell what the azimuth is, we are actually depending on solid Earth geophysics. We're depending on the fact that there's convecting metal in the Earth's outer core. And before I go on, let's just talk about how incredibly cool that is, right? So I can use a compass to find my way through the wilderness on Earth's surface because the temperature and pressure and compositional conditions way, way beneath our feet are such that we have a gigantic mass of molten metal that's moving with the viscosity approximately of water. And as it's turbulently whipping around and creating these eddies, those eddies are actually just like a curved wire, inducing magnetic fields, which then feed back on one another to eventually create the magnetic field that we have at Earth's surface. And the dipole, which is this north-south, set of poles that we have on Earth, is the strongest component of that, and that's what we use with our compasses. So we can use compasses in geomorphology thanks to solid Earth geophysics and planetary magnetism. It's pretty amazing. All right, nerd moment over. Let's continue on. So, pardon me. So here's an example of mounting a Brenton pocket transit on a tripod, and you can use that, and it has some instructions for how to properly set what's called the magnetic declination. And what is the magnetic declination? It's the fact that we don't actually, the magnetic north, which is determined by this geodynamo, is not actually the same as the geographic north. And so here we go. This is just some instructions for using a Brenton compass. You can read that on your own. But here we go right here with this figure. And what we can see is that we have these blue lines and we have these red lines. The red ones are negative and the blue ones are positive. All right, let's go back up. So the declination is east if magnetic north is east of true north. Declination is west if magnetic north is west of true north. And so over here, the negative ones here are for west. Positive ones here are for east, and you can actually just go down here and read that. So the red line shows negative west, and blue is positive east, and what that means is that all of these lines are converging on the location of the actual magnetic pole, but there's a little bit difference between a line that goes straight up to magnetic north and a line that goes straight up to true north. However, if you draw a line between true north and magnetic north, so let's just say boom, boom. They're much farther north, but that's okay. Those line between those points continues into this black line. And so for those of us who are in the mid-continent of North America, like here we are in Minneapolis, St. Paul, as I'm creating this lecture, we have this really nice street, right, in which we basically don't have to worry about declination almost at all. We are almost right on that line. It's fantastic. So one thing, though, is that magnetic compasses are accurate, but they're not always the most precise instruments. And that's due to some of the variability in the relationship between magnetic and true north and polar wander. It's also, more importantly, due to the precision in which we can read magnetic north, and especially the fact that the signal can be contaminated from magnetic sources. And it can be contaminated by sources in our own equipment, in the environment around us, or from things like, I guess human-built things in the environment, like, big power lines and steel pipes and the works. And so instead, we can often think about using an arbitrary horizontal coordinate system or something that's based on a known angle, so you're actually zeroing in your survey to a baseline of a couple of points. And so I'm just going to pop down here to these figures to show this to you because I don't need to read the whole document for you. But imagine if you have a known point and you have this known azimuth, you can actually shoot this in. And in fact, if you know what this azimuth is, if you know that between this and this azimuth, let's say, is 37.23 degrees, well, gosh, then you can start to find out that, true north is just that way. And so you can shoot that direction, get that point in, and then you have your actual set geographic coordinate system. Likewise, if you know that this point, let's say it's defined at 0, 0, and that this point is defined at 37.5, 40.2 meters. I always try to use SI. And so if we know that, then we can actually figure out, based on that point, we know what this angle should be. We shoot to that point, and then we can once again figure out that north is up here. Good deal. So in addition to these uses of total stations or some other piece of equipment to measure with this horizontal angle, we can also just bypass this whole problem of measuring angles and using trigonometry by letting satellites and computers do that for us. And so I'm just briefly introducing the fact that we have these GNSS units, GPS. I sometimes say GPS instead of GNSS, and that's because GPS is the oldest system. It's from the US, and it was the only system for quite some time. So these guys can actually are capable of measuring to a very high precision your location on the surface, and the way that they do that, so your handheld GPS, so like in a smartphone, for example, can measure to within about maybe 3 meters. It's a little screen. But for survey precision, let's take this dot I actually accidentally made. It's about 1 centimeter. And the way that it does that is by having 2 separate stations in which we have one base station here, in which we're consistently getting signals coming in from different satellites. And based on those signals, the base station position is going to appear to move, and that's because turbulence in the atmosphere is going to be changing the effective speed of light in the atmosphere. It's going to be changing arrival times of signals. And so we're going to actually have this guy, let's say that position as a function of time is going to look kind of like a jittery function. And then we have a second one that we're carrying around on a stick. Here's my favorite stick person. This one, it has a very, very long arm, but only one long arm. And so running around with this GNSS unit, and it's going to have a lot of error too. But then we look at this big wiggle and we subtract this wiggle out from that wiggle, and then we actually get an extraordinarily precise position from this station because we've taken care of the error that's associated with atmospheric turbulence and larger systemic variables, and so we can compare this system directly against this one. And that's why if you have a base station and a rover, you're capable of using this differencing approach to then obtain extremely precise positions in what's called either differential for post-processing or real-time kinematic if you process it during the survey GNSS. All right, back to the ground-based instruments. So you can measure angle and distance together. And measuring angle and distance together often works by using a specially equipped laser rangefinder or an aptly named total station that does azimuth, inclination, and distance. So here's our quick little picture of, yay, GNSS units. And the third option for getting both angles, so both azimuth and inclination, as well as distance, is a terrestrial laser scanner, which is just a machine that has spinny parts that will take an entire sphere of distance and orientation measurements. And all that together can be used to stitch together a fully three-dimensional image of a region on Earth. It's a really fantastic piece of information and a really great piece of instrumentation as well. So here I'm just kind of going over the different types of these instruments. That's not so important. The main important thing is that this is a prism, and this is retroreflective, meaning that whatever orientation, if you're shooting in from this orientation or from this orientation, the light is going to bounce straight back at you. And so it's not like, if I'm looking in a mirror and I'm standing to the right of it, I actually end up seeing the reflections that are coming off from the left of it. It's the kind of thing where if wherever you are, it actually is following you. And so we use this as our target and we shoot lasers at it. So the following pieces are just about setting up a particular total station. So these are the Nikon ones that we have at the University of Minnesota. This kind of Nikon total station is a pretty decent basic model, reasonable precision, and so you have this eyepiece here, a sight here, some controls down here. This is the side that has the objective, so this is actually a telescopic lens. You might notice this is made by Nikon, right? And so that's what you have, a essentially telephoto lens, except it's a telescopic lens that then ends up showing you where you're going to shoot a laser. Kind of cool. And I have a bunch of information if you need to start a survey. If you want to read through this can be actually quite useful. But because we're not actually able to go to the field this year, forgot a paren. Because we're not actually able to go in the field together this year, we're not going to be worrying about this too much. It might be that in a future year, if this video is still around, I tell you to ignore what I say and to pay a lot of attention to it. But this is a good reference guide. I often give this reference guide out to colleagues who are going out in the field to survey. So just hang on to it and use it as it's useful to you. So with that, I'm going to save what I've doodled on here, post this up on the internet as well, along with the undoodled notes, and let you look through this to figure out how to work with the data. And also just to think about how surveying works in general. And one final note is that after you get the data out of the total station, you can then plot them either in something like a spreadsheet or in, I would suggest, a geographic information system. We'll talk about those quite soon. And these GIS softwares or geographic information systems are incredibly useful for organizing geospatial data and for being able to plot different types of data and different data sets on top of each other. So with that, that's sort of your slapdash introduction by just quickly running through these notes, or I guess sort of quickly, on how land surveying works and how we measure Earth's surface.